Hi, everybody. I'm Francesca Rossi. I work at IBM Research. I'm the company AI Ethics Global Leader, and I'm also the past president of AAAI. And I would like to welcome you to the AAAI panel discussion on AI reasoning. Before we get to the discussion, let me say more generally what AAAI did around AI research recently. So we observed that AI capabilities and research were undergoing and are still undergoing a fast and very significant transformation along many dimensions, the topics, the methods, the research community members, and the working environment. So it's very important to be able to clearly identify the trajectories of AI and AI research and the challenges still ahead of us to make AI more capable, reliable, and safe. So to contribute to this goal, in March 2025, during the AAAI conference, AAAI published a report on the future of AI research, which summarizes the finding of a study of several months on significant AI research trends. The study was conducted by 25 prominent researchers and supported also by a community survey with about 500 respondents. And it covered many of these trends that I mentioned. Who is doing AI research? What new topic in AI is AI research about? How AI research is conducted? And also mentioned the geopolitical scenario that globally is enabling and supporting AI research. This report has been intentionally written in a non-technical way because it's intended to reach other audiences, not just AI researchers, including experts of other disciplines, policymakers, funding agencies, the media, and the general public. You can find the report on the AAAI website, and you will see that it has identified in total 17 topics, and it has a chapter on each one of them. And each chapter sketches the history of this topic, the current trends, the open challenges, and also what the community survey reports about this topic. Uh, to follow up this report, we already held two discussions on two of the 17 topics, one on AGI and one on AI perception versus reality. And today we will discuss the topic of AI reasoning. Of course, reasoning has always been seen as a core characteristic of human intelligence, is used to derive new information from given knowledge, and this new information is correct when sound formal reasoning is used. Otherwise, we can say is plausible information. Since AI is also mostly, but also trying to imitate human intelligence, it's no surprise that AI researchers have tried to embed reasoning, human reasoning, in AI systems. However, it's also important not just to mimic AI, not just to mimic human intelligence, but also we want the technology to be reliable. Therefore, there is also a critical need for verifiable and sound reasoning in AI systems. Over the decades, AI research has led to a range of automated reasoning techniques that have given rise to AI algorithms and systems, including SAT, SMT, constraint solvers, probabilistic graphical model, all of which have played and continue to play a key role in critical real-world application. More recently, with large pre-trained systems like LLMs, they have made impressive advancement in their reasoning capabilities, but their reasoning appears less sound and correct or more like plausible. And so more research is needed if we want to guarantee correctness and depth by the reasoning performed by them. And such guarantees are particularly important for high stakes decision scenarios and for autonomous AI agents. So let me introduce the panelists of today's discussions. One is Olga Rus. Olga is an Alexander von Humboldt Professor for AI at RWTH Aachen University in Germany. Is also a professor of machine learning at Leiden University in the Netherlands. Is the president of the European AI Association, EuroAI. Is the chair of the board of CARN, Confederation of Laboratories for AI Research in Europe, is a fellow of AAAI, EuroAI, ACM, and is an expert in machine learning, automated reasoning, and optimization. The second panelist is Subba Rao, Rao for friends and everybody, Kambapati. He's a professor of computer science at Arizona State University. His research is mostly around planning and reasoning capabilities of large language models or large reasoning models. He's a fellow of AAAI, ACM, AAAS, and the former president of AAAI. Rao is also the recipient of this year's AAAI Outstanding Educator Award and is very active on Twitter, X, and LinkedIn explaining AI concepts. So before we start with the questions to the panelists, let me remind everybody to write your questions in chat. We will try to address them possibly towards the end of the panel discussion. So let's start with Rao. So let's start from the basic here about reasoning, because many AI papers, and I'm sure the audience have seen them, claim that AI is able to reason, but many others claim that it's not able to reason. So it seems to me that the reason for this discrepancy may be in the different definition of reasoning that the authors of the paper use. So let's start from there. What exactly is reasoning according to you, and what role does it play in human intelligence?
Yeah, so in Intro to AI, we talk about the fact that in especially most formal systems, you start with some base facts and you are able to find the inference from them. And the idea of finding, doing inference to reach valid conclusions or plausible conclusions in some cases or probabilistic conclusions has been seen as reasoning. And the interesting part, of course, as you mentioned in the beginning itself, reasoning is what AI was doing from the beginning. And if you start from general problem solver, GPS, and all the things that Newell and Simon, etc., were doing, they were essentially in the business of giving the base facts that the humans will write down and then focusing on can the AI systems do long chains of inference with some guarantees, which is part of reason why we were able to actually have a chess machine winning over human human champion Garry Kasparov back in late 90s, right? What changed is those systems were sort of deep and narrow systems. They would start with some knowledge that you have written, you have acquired and written for the AI system. And then the system itself focuses more on the inference part. And starting like 2013 onwards, we sort of gotten very much interested in these pre-trained large language models, which essentially have been trained on the entire digital footprints of the humanity. And so the question then is, are they somehow going to be able to, of course, when you do train that, they will be able to integrate pieces of information, provide shallow inference on this broad knowledge they've been trained on. The real question is, are they actually able to actually do long chain reasoning? The answer for that turned out to be that the normal LLMs couldn't. But then if you actually somehow also train them on the reasoning traces, which is what has been called LRMs, starting O1 and so on, they can actually imitate some parts of the reasoning performance. And the way I'd like to say this is, originally, LLMs have been trained on the knowledge web that we wrote for each other. And what now we are doing is we are kind of creating a synthetic web where with a huge number of problems on their solutions. And then you're training the LLMs on those too. And that's partly the way we are imitating reasoning in these kinds of systems.
Okay, Olger, but before we go to AI reasoning, so tell me your opinion about what reasoning is, and then should be maybe when we try to imitate it.
It's a fascinating question, right? And I think it is one that even philosophers haven't fully answered. Rao already mentioned there's actually different kinds of reasoning. Even in philosophy, there's different kinds of reasonings that are being distinguished from each other, such as inductive reasoning, deductive reasoning in particular, right? And so I think it's really important to be aware of the fact that reasoning is sort of a distinct achievement of human culture, right? You can trace this back way before the period where any sort of higher technology emerges. For instance, in ancient Greece, philosophers spent a lot of time thinking about correct modes of reasoning. And as Rao said earlier, correct modes of reasoning are those that basically from premises that you believe in for whatever reason, because, for example, you've observed something in nature, right, can give you deductions, can give you further statements that then turn out to be reliable and true, right? And now, of course, whereas the ancient Greeks have mostly been concerned with a kind of deductive reasoning that is very deterministic, right? So you assume that you have some facts, you have these basically rules of reasoning, and you derive new true facts from them with certainty. Of course, later on, it's been realized that there are other kinds of situations where you can't be entirely sure about the knowledge that you have, where you have to deal with uncertainty and so on. And much progress has been made over the centuries to basically get to more general modes of reasoning. And then, of course, there is what you might call common sense reasoning. It's basically what people use in order to deal with everyday situations without resorting to any sort of formally trained logic, right? And so what I would like to say, maybe a little bit provocatively, is that this idea that you get good reasoning, the kind of reasoning that as humans we use all the time, for instance, in engineering or in mathematics, right? The first thing to realize is that people aren't very good at this. It's very hard for people to learn this, and therefore it's been a great cultural achievement to understand the basics of these kind of reasonings. And we've been working on them for more than 2,000 years. And we should be very proud of ourselves that we figured out basically as human societies to reason well enough that we can base technology on that. And computers in particular wouldn't exist if it weren't for that kind of, I would call that logical, formal reasoning with guarantees. In some sense, you can see computers as the embodiment of that sort of logical reasoning, right? And so for that reason, it seems a little strange to me that nowadays, many people with superficial knowledge of AI, and even some people with very deep knowledge of AI as a field, seem to be content in saying, surely if we just train on enough data and we have a model that's complex enough, reasoning will somehow magically emerge, just as it did with humans. I think it didn't magically emerge with humans. I think it was the effort of a very long and complex cultural process. And any of us here, I think that's Rao, that's you, Francesca, that's myself, and that's probably many in the audience as well, who've had anything to do with teaching students to think logically, right? Know that it is not a natural thing. It's something that you have to study and learn and try very hard at before you get even reasonably good. And then machines from the very beginning by design have always been better at it than we have, right? Not at the level of, grand mastery in chess, but at the level of just forming long chains of the kind of reasoning steps you need, for instance, for arithmetics. And just to conclude this little part with that, I mean, you don't have to look at sort of deep logical reasonings to find limitations of current large language models and also large reasoning models. You can go to simple arithmetics and you find that they can't do that very well, because that too requires some sort of formal reasoning that they're just not made for and that they're not good at.
Yeah. So to follow up on this question, tell us, I mean, especially for very young people in the AI research community that may not be aware of some success stories of AI reasoning in the past, or of sound and correct reasoning embedded in AI systems. Maybe you can tell us a little bit more about some of these success stories. After all, of the respondents of our survey, I think that 79, almost 80% of them indicated that the topic of reasoning is relevant to their research. But maybe some of them are not aware of these success stories of sound research, sound reasoning that AI research has produced and used to build computer and systems that we still use today. Can you say something about that, Holger?
Sure, I'll try to keep it brief because I know that Rao has a lot to say about that since he's an expert on many things, including AI planning, which is one of the domains where there have been a lot of successes and continue to be. So let me just briefly mention something else. We wouldn't have any of the hardware that we currently use, not just for AI, so that's GPU, CPUs, and so on, but also for our mobile devices, for pretty much everything that's driving our banking system, our public administration, the computers we use for research and engineering and so on, right? We wouldn't have any of this if it weren't for AI reasoning techniques such as SAT and SMT solvers, because they're used in order to verify, in many cases, not completely, but in key parts, the hardware that we're using at tremendous scale. So, take NVIDIA. NVIDIA wouldn't be possible. Their products wouldn't be possible. The way we use their GPUs would be completely impossible without AI reasoning techniques being used to verify major parts of the chips that they're producing. And that, I would actually claim, is the biggest success that AI has produced so far. The ability to build microchips, electronic circuitry of a complexity that no human or team of humans could handle possibly. At least not in a way so that we can trust these things, and still have that and use it and rely on that in critical applications if it weren't for these kind of AI reasoning techniques.
Thank you. Rao, do you want to add anything about planning or anything?
Yeah, I mean, in general, I can actually say that, the planning techniques have been used by NASA. Mission planning is mostly using probably correct planning techniques and so on, model-based reasoning. But I also want to kind of mention the following thing, that much of computer science, really, algorithmic reasoning is a very strong form of reasoning. Certain types of algorithmic reasoning has actually become the purview of what people called AI. But, like SAT, for example, satisfiability is something that, there are algorithms. Davis-Putnam procedure is, in fact, one of the earliest JSCM papers. The one thing that I want to mention is, while it is important to think about deep and narrow systems, which AI was very good at before the onset of the LLMs and broad and shallow stuff, it is also useful to actually have this jack of all trades, which basically can, in fact, we'll talk more about it, I'm sure, as we go on. They can provide sort of reasoning shortcuts for somebody who is in the loop, especially either a formal reasoner or humans in the loop. They can provide ideas and shortcuts, which, as long as somebody else can directly, they can actually verify, they are great idea generating machines. And so we may be able to find uses for this sort of shallow, plausible reasoning, even if it's not guaranteed correct. My only worry would be when people say, let's just put them in the end user facing safety critical scenarios and see what happens. And that see what happens would not be very pretty, because there would actually be, without guarantees, essentially there can be very costly failures.
Yeah, so let's go a little bit deeper into that. So because we said that we have these two forms of reasoning. One is sound and correct, one is just plausible. Symbolic AI has produced a sound reasoning system. Modern LLMs can perform instead plausible reasoning. When we asked in the survey to the community about properties that they would like to see in a process to be called reasoning, 77% of them said that knowledge should be incorporated, 72.5% that explanations should be provided, and 57% said that it should involve multiple steps to arrive at a conclusion, but only 37.4% said that there should be guaranteed correctness of inference results and outcomes. And only 23.7% said that a formal system and solver should be used. So it seems to imply here that there is really a recent focus on informal, plausible reasoning more than on sound reasoning. So let's go a little bit deeper about whether one form of reasoning is better than another one, or there is space for both in different scenarios. And also that after all, this plausible reasoning is what human reasoning is, and emerges from our brain. We don't have some reasoning rules written in our brain. So isn't that similar to what happens with LLMs? So where do we use, where should we use one or the other form of reasoning that now AI can provide? Do you want to start, Rao?
Yeah, so first of all, as you mentioned, and I'd actually say the following thing, that even before the broad and shallow systems like LLMs, we have had and looked at plausible reasoning. Analogical reasoning is a famously plausible reasoning. We realize that plausible reasoning is extremely important. One of the ideas is, I keep telling people that you should let your ideas come from anywhere, but then you want to prove if in fact safety matters, then the idea that you have, you may actually have to check whether it's actually correct. So if you kind of limit yourself to only having correct ideas, then you won't think much at all. And that's sort of the part that was known before, even within plausible reasoning in the AI and cognitive science. And what is interesting is plausible reasoning and analogy is something that LLMs are actually pretty good at doing to some extent, mostly because they've been trained on the entire collection of human knowledge, at least as we have uploaded it to the web. We never had something like this. As you might know, some of you guys old enough to remember, Doug Leonard tried to do this thing of let me write it by hand. And the problem is it becomes extremely hard. What happened with the web is everybody did whatever the heck they wanted in natural language. And we have these machines that do a reasonable shallow inference on these kinds of knowledge. The interesting part is, and in fact, even factual knowledge that LLMs produce is only plausible. That's where your huge hallucination points come along. So they can't even actually directly, with guarantees, answer factual reasoning. If you want factual reasoning, you can always go back to the boring databases. They will never make up stuff. But on the other hand, there's a good thing to talk about how to combine all sorts of pieces of information. I'm pretty sure a lot of us are actually dependent to some extent on these AI overviews when you do search, because you are still in the loop, and that AI overview might actually provide you interesting way of combining pieces. The thing that is interesting is, how do you go from plausible reasoning to reasoning that has soundness guarantees? There are some obvious ways. One idea is to generate and test. And as Holger was saying, and we were talking about earlier, much of classical computer science and artificial intelligence has been focused on providing principled solvers and verifiers. And in fact, those verifiers are extremely useful. You can actually have a SAT verifier that if you say, here is a particular satisfiability assignment, the verifier can check if in fact it's a correct assignment. And you can let the LLMs come up with suggestions, and then the verifier checks. This is a way in which you can actually easily provide correctness guarantees. And one other thing that has been actually called test time scaling in the current LLM literature. The other thing is, as Minsky said, part of intelligence, much of intelligence is take the test part of generate test and put it in the generate part as much as possible. And that's what has been called post-training in LLMs. So in essence, you kind of train the LLM with verifier-based reasoning during the training itself, so that the kinds of suggestions it makes are more likely to be closer to correct. But still, there is no guarantees unless, again, you have verifiers in the loop. The very interesting thing this brings up, in essence, is LLMs are amazingly good at capturing the style of anything that they have been trained on. And that's something that we have seen, that things like Shakespearean iambic pentameter is so easy for them, and it's so darn hard for us. And so one of the interesting questions was, if you show them enough algorithms, and after all, human web, the web that we created does have algorithms. Wikipedia has algorithms. Can LLMs can just do internally simulate algorithms? The answer is no, they couldn't, which is actually why the standard LLMs, basically, for which there were lots of claims that they can do reasoning, they kind of got replaced by these quote unquote reasoning models. If in fact the original ones are doing reasoning, then you don't need reasoning models. And so even the people who say that they can do reasoning admit that they weren't doing reasoning. And the way now they are doing reasoning now is not, you can't just read an algorithm and execute it. Instead, you use the algorithm or a verifier to actually generate multiple traces and see which of them are correct, and train the LLM on that. And that is a very inefficient way of training the reasoning in, but it is something that you are not paying for, because somebody else with large amounts of reasoning infrastructure, GPU infrastructure is doing it. And for you, the end user, right now, it's not costly. And so it will actually improve the plausibility of the inference, but without guarantees still.
Thanks. Olga, do you want to comment on this use of the two form of reasoning, whether they're useful, one is better than another one, and the relationship with this idea that plausible reasoning, like in LLM, emerges just like it emerges from our brain?
So I think it's possible that plausible reasoning, the shallow form with no guarantees, heuristic reasoning emerges, right? That's about as plausible as kids picking it up without any formal instruction ever, and I think there's some evidence that they do, right? I mean, there are even some other species that, without sort of any form of cultural transmission, apparently can master tasks that require a few steps of reasoning. But that's actually not the question. The question is, how deep and how reliable does the reasoning have to be in order to do certain important things? And here I think it's very important to realize that one of the ways in which generative AI, LLMs, large reasoning models are being used increasingly as we speak is for generating computer code, right? I'm not even talking about inventing new algorithms. I'm talking about coding and software engineering tasks related to that. And in fact, it has been argued that this is one of the ways in which this technology brings the most immediate value. And of course, we all know that it's difficult to train good programmers, and there is already a shortage, and that shortage is going to get worse. So therefore, I think it's very important to talk about this elephant in the room. Can this technology, LLMs, large reasoning models, be good enough at the kind of reasoning you need in order to use them for coding? And actually, we're doing a bit of research on this at my institute. I think Rao has looked pretty deeply into that as well, and so have many others. And I guess what we see is not surprising at all. It is you need actually pretty deep and sophisticated reasoning with guarantees in order to make correct software that's free of vulnerabilities, and software that's reasonably efficient is then, of course, even harder, right? And so the question is not so much, can LLMs help expert coders be more efficient, although there's even some uncertainty about that. You might have seen there's contradictory recent studies on that topic. But the real question is, can that be used in order to have non-expert coders replace what currently expert coders are used for? And I think the answer is, if you just look at the evidence, a very much resounding no. Yesterday, there was a major security issue coming from Microsoft, actually, from SharePoint. I think many of you will have heard about that. That is something deeply concerning. And of course, we have no idea whether that was a result of any AI coding techniques being used. But what I would say and what I would speculate in an educated way is, if we continue to go down that path where we ignore the requirements of, relatively deep and sophisticated logical and mathematical thinking when generating computer code and software, we will have a lot more problems like this in the near future. And that, I think, is a great concern. I think that could, in fact, sink the entire AI boom that we currently have. Because just imagine a world in which computer systems become even less reliable than they tend to be even nowadays sometimes, right? I don't think that would be particularly good. In fact, a lot of what we do at universities and other places that train people who build systems is, of course, to make them better at building systems that perform according to specs and that have no vulnerability. So my feeling is that what we should spend effort on is actually making these people more effective in what they do. And I'm not sure we're doing it sort of blasting down the path that's currently being laid out in front of us, believing somewhat blindly and without good evidence, I would say, that the kind of formal reasoning that's needed in order to have success there somehow magically emerges along the way if we just train these things more smartly. I think that's pretty naive.
Yeah. So you also touched upon the collaboration between humans and machines that we will elaborate more later on. But now let's also focus on, there are a lot of benchmarks that try to check whether these AI systems are reasoning or not. And if you pass the test, then researchers say that they're reasoning, otherwise they're not. So how should AI reasoning actually be tested? Are the current benchmarks good enough? Should we think of new ones? And if there are new ones, what properties should these benchmarks be to be good benchmark tests for AI reasoning? Rao, do you have thoughts about that?
Yeah, so before I get into the benchmarks, let me just respond to one thing that Holger said, and I would do, without contradicting anything that Holger said, let me just say that the progress is not that bad. Honestly, it's actually the ignorance that might be worrisome to Holger, that people who might be thinking that LLMs and LRMs have properties that they don't, but they themselves are magical and useful for humanity right now. So if you think in terms of retrieval on one end and reasoning on the other hand, LLMs come to like approximate retrieval, LRMs kind of come to approximate reasoning, and it's a useful advantage to have these highly broad but no guarantee systems for lots and lots of applications. When again, if you put them right in front of safety critical or end user facing applications, you get what you deserve, and there is no reason to feel sorry for you at that point. But on the other hand, I do actually think that getting broad and shallow models to be little deeper is a very useful research direction, and that is indeed what is happening in the LRMs right now. Again, no research is ever goes in one single step, and so there are obviously all sorts of mistakes that are currently happening. For example, that these reasoning systems, LRMs, tend to provide intermediate tokens before giving the solution. And there has been a mythos that developed that these intermediate tokens are thoughts that LLM is entertaining. And there's actually no real reason to believe that whatsoever. It turns out that we have work, for example, there is a paper from a group on Beyond Semantics that people can look at, that as well as a position paper that kind of argues that the intermediate tokens are helpful to the LLMs, but they don't necessarily have to be helpful to the humans at all. And trying to make sense of these intermediate tokens is like looking at Rorschach test, ink blot tests, and saying, oh, there is an elephant there, there's a parrot there. You are seeing it. They are not there. So that's the first point. Coming back to benchmark, this has been a very interesting problem about LLMs in general. Now, machine learning has always known that if you train a system on a particular distribution, when you are testing, you should make sure that the test data is from the same distribution or out of distribution, but not exactly the data that you're trained on, because that would be just memorization. But when you are training these systems that are being trained on the entire universe of data that is available, there is no such thing as out of distribution. What is today's benchmark becomes tomorrow's training data. This has become very much clear with things like MMLU, etc., which started as reasonable benchmarks. And now everybody knows that the systems have been trained on this data, whether it's deliberately or by actually accident. And so in general, one thing that people really need to understand about LLMs and LRMs is their capabilities are basically memory effects, the stuff that they have been trained on. And we have it's very hard to completely characterize what things the LLMs have seen, what things they have not seen, because of which this famous thing about jagged intelligence comes, that they can, for example, solve something like integration by parts and fail on a multiplication problem, while you'll never see a human that can do the integration by parts and fail on multiplication. It's because what is present in the memory. So we actually did a recent study that shows, for example, that if you train a transformer on complex mazes, and it does well on that sort of complex mazes, and then you ask it to solve problems where there is no maze, that means it's actually free space, start and goal is right in front of each other, it dies. And in fact, it has nothing to do with the computational complexity. LLMs and LRMs don't solve problems in the classical computational complexity way. They're solving in terms of the distributional distance between what they have and what they're trying to solve. And in general, because we did this for like carefully constructed, training and testing, but normal LLMs right now, essentially everything has been seen by them. In fact, yesterday we talked about IMO stuff and so on. There's huge amounts of IMO data, International Mathematics Olympiad data, that's been fed into LLMs. And so they are a kind of a memory effects. And I tend to say that LLMs are good at humanity's knowledge closure. So if you think of entire humanity, they can do shallow closure of that knowledge, but not like, basically the reasoning parts can get you there. And then the farther it goes from the closure, the farther it goes from the humanity's current knowledge, the harder they are, the worse their performance is. And
Yeah.
so
So
it's, go
yeah.
ahead.
Now, before I give it to Olga, I wanted to comment on what you said, because it's not really the entire humanity knowledge, it's what is represented on the
Yes,
web,
yes.
which for some cultures is much less compared to other ones. So there
But
are
certainly
some
it is, but it's
parts of
certainly,
the entire parts of the world where the connectivity, for example, is much, much less. So of course, there is less representation on the web.
yes, except that it's by comparison to,
No, of
pre-trained
course,
model
of course.
thing, this is way closer to the entire
Yeah,
humanity's knowledge than.
But we
Yeah.
have to be aware that
Mhm.
not everybody is equally represented on this knowledge on which the LLM build the closure. Olga, go ahead.
And furthermore, I think we have to be aware that really, if you truly train something on everything that's out there, it's likely that you get inconsistencies, of course, right? I don't think what you call the knowledge closure of humanity, Rao, is in fact so desirable in the sense that from a purely logical mechanistic point of view, it's likely going to be inconsistent and full of errors, right? And of course, you train on that too. However, I think there's one point that you made that I really want to just emphasize a little bit more, and that is, because current generative AI technology to a large degree at the bleeding edge is proprietary, and we don't know really precisely what data it's been trained on and what training procedures have been used and so on, right? It's actually quite difficult, even for somebody who has the best intentions and lots of resources, to explore the limits of this, right? It's basically it's a lot of black and blackish gray box evaluation of these systems. And I really think it shouldn't have to be that way, right? Sure, this is the way we test human knowledge as well, but let's be very honest. What we don't know, what we don't need actually is sort of more systems that have all the problems that people have in the work they do. It shouldn't be about replacing people in all sorts of activities that they may be good or not so good at. It should really be about helping people deal with problems that perhaps they're not so good at efficiently, or help them, do more of the stuff that they could do without the systems, without replicating all the problems that typical humans would have, right? And we know perfectly well that students who, for instance, cram for exams will typically not arrive at deep understanding and will display some of the same sort of problematic patterns of performance that we see in generative models, right? And we also know what it usually takes to get students further. And we don't even have to talk about university students. The same applies even for high school students and for kids at lower levels of schooling. So my feeling is that absolutely the current technology is very useful. There's no question about that. But it's crucial that we spend more effort at understanding the limitations and then being very open and transparent about the limitations and enabling those who are not AI experts and who can't do these sort of experiments and testing for themselves to make smart and responsible decisions about their use of the technology. And Raul was entirely correct in suspecting that this is what I'm really worried about, because I can see this happening right now. Not so smart choices being made because of a combination of marketing by certain players, and of course that's it's understandable that companies want to sell their products. That's perfectly fine, actually, right? But then they're also not being enough sort of unbiased views on what this stuff is actually good for. And I do think there we need a bit of a correction. And reasoning is one of the areas where the where it's really problematic. And it's problematic because reasoning is what you need in order to get guarantees where they matter. And of course, Rao said correctly, not everywhere guarantees are crucial, right? But there are many places in society where we need guarantees. And it's not just safety critical stuff like, running parts of our banking system or running nuclear power plants or anything like that. It's much more mundane and smaller things. I mean, think of the software that is being used, for instance, by the tax authorities. What a disaster it would be if that software were, of lesser quality than we have today for everyone, right? And so I think we need to get smarter in understanding where guarantees matter. And just as a final thought on this, there are many, many areas where machine learning technology is used. For example, in the medical field, where robustness matters greatly, right? And reasoning techniques are also absolutely key in ascertaining robustness of machine learning techniques. And these reasoning techniques that are being used today are thankfully not really large reasoning model based or large language model based, because that wouldn't be sufficient at all, right? So they are of the different flavor that AI thankfully also has in stock. And in fact, if you combine these things together, you get already significantly added value today, right? In the form of more robust machine learning models. So that is another direction that I think is extremely important for people to understand, can bring value to the entire enterprise and can make the machine learning methods that we use actually more responsibly applicable in certain areas, such as medicine, finance, and engineering, and so on.
Yeah, so you touched upon this, and both of you, about the relationship between human and LLM kind of reasoning and other AI kind of reasoning, because especially with LLMs, as you know, there is also this personification, this anthropomorphization of LLMs. LLMs write like a human being, so people tend to think that they also have other characteristics of human beings, such as reasoning also, and logic reasoning. And so that's really can create some confusion about what an AI system can provide. And maybe it's not what it can provide because it has a different form of reasoning. Even knowing that, in our survey in our community, about almost 42% of people that says that focusing research in AI on human level reasoning is valuable, or 47% they say even essential. So is that really essential according to you, that that AI can try to simulate human reasoning, or it should just provide a different form of reasoning and we should not try to imitate and emulate human reasoning? Proud, you want to
Maybe
start?
I'll start quickly.
Yeah,
Maybe
sure.
I'll start quickly because it directly connects into what I said before. So let me try even crisper. I think it's a mistake to focus research on reasoning, on trying to imitate human reasoning, because human reasoning is quite weak and fallible, right? So what we've achieved over the past 50, 100 years is to actually develop techniques that are better than human reasoning, that are by leaps and bounds better. And these ways have allowed us to build the technology that's underlying all of AI and all of computer science and all of its applications today. So therefore, merely reaching human levels of reasoning would be a very low bar, a problematically low bar. What we need to do is reach the levels of reasoning, or actually just make sure that they're not forgotten about and that they're applied when they're needed, that we already have, and then maybe further improve on them. And I don't think teaching large models how to reason is the best way to get there, but one can, of course, have a meaningful debate about that, right? But the most important thing from my perspective is to realize it needs more than human reasoning to do a lot of things that we're already doing quite well that are essential. And that more than human reasoning doesn't come from generative AI nowadays, nor is there any evidence that it will come from it in the near future. So let's use what we have. Let's try to use it in meaningful combinations with this other kind of AI, right? And of course, that gets us to the point, why should we have one model that does it all? Why don't we plug things together so that, the right tool is used for the right job?
Yeah, Rao.
Yeah, so I agree with the part that if civilization depended only on individual human reasoning, not about the scale effects of human civilization, we would still be in beautifully decorated caves, not having these Zoom conversations, etc., etc. I mean, human civilization is has a much bigger scale effect than what individual human that you can pick off the street might or might not be able to do. The interesting point here is people actually confuse this from even the more LLM supportive side. They both actually say, when, for example, you say LLMs don't do multiplication, that, and have you seen humans who can do 20 by 20 digit multiplication, and also take credit for the fact that LLMs and LRMs can do well in International Mathematics Olympiad, which about 7 or 20 people actually even understand those questions. And that's not really very human-like, I would say, in terms of normal human-like. In general, what we really want is support for reasoning of all kinds, and then with guarantees. I once again still think that it is extremely useful that this technology exists because we never before had this ability to bring to bear tons and tons of knowledge that's all over the place, and then basically see what you can get from shallow inference or slightly increasing length inference from that sort of knowledge, and so they can actually force multiply our productivity in multiple ways. The most important thing, and I hope this particular panel and other panels like this will help, is understanding, having healthy skepticism rather than be overly optimistic and overly pessimistic about these models. I mean, remember, AI used to be a thing that only people that will go to either AAAI or NeurIPS would talk about. Right now, your grandmother and your grandfather know more about AI than you know, in terms of, at least from the news perspective. And so it sort of becomes, it also comes with the territory, with this great success we have, that there is significant misunderstandings about what the technology is able to do, and it's sort of very useful to understand those distinctions. And I do want to point out one crisp distinction, that the current LRMs are actually still still have that limitation. We have shown this as soon as O1 came, and there's a TMLR paper on that, which is, think of something extremely simple. Don't talk about planning, don't talk about SAT, nothing. Think of this thing called last letter concatenation. If I give you 3 words, then you are supposed to take the last letter of each of the words and make it into a string. You understood this now. Now, if I again give you another 3 words, you can answer this. If I give you 10 words, you can still answer this. If I give you 25 words, you can still answer that. What we see with LRMs, and of course also in LLMs, is that they will do well at the place where you gave the size of the last letter concatenation examples you gave. If you gave like 3-4 letter examples, they will do well at 3-4 letter examples. They will die as it becomes 10-20. What that tells you, and this has been seen across the board in planning and reasoning problems, what that tells you is that they don't learn algorithms directly, they learn unrollings of the algorithms. So they are basically, I'm good for 4x4 last letter concatenation problems. I am good for 3x3 digit multiplications. This we will laugh at, because we'll say that kids are supposed to understand how to do multiplication and follow that procedure, however boring it is. But LLMs are not actually good at following procedures. They're not learning algorithms, they're learning unrollings of these algorithms. And it's a very useful thing, because the reason they do that is because that makes it easier to combine that into the current training regime of LLMs. Each of these unrolling things, if you look at, for example, DeepSeek R1, it tries to solve, it starts with a base model that has what is called top 15 accuracy, that is reasonable in the sense if it makes 15 guesses with 90% success, one of them is the correct answer. And then it gives itself new problems, tries to guess their solutions. The verifier checks which ones are correct. And this laborious RL process tries to improve this base model. When you do this, it actually has a slightly better top 15 accuracy on larger problems, but then it becomes again 0 when you go further about that. And so you have to retrain it again. This is something that actually people have to understand, that they're not learning algorithms, they're learning unrollings of the algorithms, because most of this is a computer science crowd. They will understand that distinction. And by the way, this is what actually got repeated by this Apple study. We wrote this actually back in TMLR has the paper, but we did in September. But they actually wind up showing the same thing, that as you increase the length of the blocks world planning problems, it will finally die, et cetera, because basically they are unable to follow any procedure.
Olga, yes.
And just to connect to that, that is precisely why they can't solve non-trivial programming problems, right? Because you need loops for that, right? And the loops better not be sort of depth bounded so extremely. And that's also why they will not be particularly good at doing science in the foreseeable future, right? Because that also needs more than just learning from length bounded examples. I'd like to come back to one point that you made earlier, Raul, which I think is interesting and insightful, and that is this remark about computational complexity, right? And without going into any technical details here, I mean, we know and have reasons to believe, computer scientists have worked on this for a very long time, and excellent mathematicians as well, that there are interesting problems in the world, many that require great complexity to solve in their generality, right? So many of the ones that you mentioned, Rao, fall into that category. Many types of programming tasks fall into that category as well. And there's no reason whatsoever to believe right now that there should be major shortcuts to this. And it would, of course, be the case that, even if very, very large reasoning models were capable of solving these problems in their generality, it would be the case that we would have basically shown that these problems are not nearly as complex as we think. And I think for very deep theoretical reasons, one should be doubtful of something like that. Doesn't mean that it can't be true, but it means that the burden of proof, the standard for proving something like this or for making people believe it, should be very, very high indeed. And to me, that also indicates that we need to get even better than we already are in talking about the tasks that AI techniques that have been developed over the last 30, 20, 40, 50, 60 years and are being used very successfully in practice will not likely be simply replaced by at least the current kind of LLM and LRM technology. I think it's very important to understand these sort of that there are these deeper reasons, even if not everybody can follow the deeper reasons, but they do exist. And I think even the trained computer scientists who make other claims would not go as far as saying this is now evidence that these problems aren't as complex as people have thought, because I think people would stop taking them seriously. The real risk, of course, is also what Rao said earlier, that now where everybody talks about AI, and it's no longer just a subject of expert conversations, we have very influential people like Obama is one of them, who start making claims about the capabilities of AI systems, and people believe these claims simply because somebody who they respect and trust in many ways has made the claim, right? So it's very important in this sort of situation to understand that there's a difference when experts that are really trained computer scientists and trained AI people make claims, and somebody who might be very famous or might be a CEO of a big company makes claims. There is a difference there, right? The difference is not that one is surely right and the other is surely wrong, but the difference is that one of them has more of the background one needs to even know whether something is right or wrong, whereas the other has to rely on secondhand information.
Okay, so I think that we have analyzed many dimensions. Sorry, Rao, do you want to say something else?
I just wanted to add one thing. One of the nice things about doing this for AAAI is we have the great people in the audience. Ron Brackman pointed out something that I've been saying separately. When you have the web, you can have explicit or declarative knowledge or procedural knowledge, and LLMs are actually not, the unrolling aspect can be thought of in terms of they're unable to unroll the procedures. They're not actually learning the procedure directly. And so that is part of the current limitation of LRMs, and that's what you laboriously use RL post-training to increase the inference horizon. So in a way, the signal in the verifier, which actually checks whether the plan is correct or not, that for any length of the plan, is slowly being compiled into the generator in this incremental, horizon extension, which could be fine if in fact you never want to do more than, let's say, 100 by 100 last letter, 100 by 100 word last letter concatenation problems. But one of the things is, as we know in computer science, the final answer might well wind up having some very repetitive computation lower down. And if you fail there, you will get the wrong answer here, even if in fact this doesn't have those many rollings. In general, it's too early to give up on all your computer science background. Keep that and understand LLMs, LRMs, which I think is what much of this panel is really saying.
Yeah. So I actually have a follow-up question on what you said, Rao, and mentioning also what Ron wrote in the chat about explicit and implicit knowledge, because at some point I thought that symbolic AI was more about the handling of explicit knowledge, and machine learning and LLM were more about implicit knowledge. Because they were not symbolic. And also, we discussed at length, the system one, system two analogy with the thinking fast and slow theory of human decision making, where the system one is more like implicit knowledge and system two is more like explicit knowledge. And usually system one is more thought to be similar to LLMs, while system two is more similar to a symbolic AI system. So how do you reconcile this observation that instead LLMs are better able to deal with implicit knowledge rather than explicit one?
Can I take this?
Yeah, sure.
I would say something slightly controversial for this crowd, at least, that I think the symbolic is red herring. It's not, the question is, you could essentially have a neurally compiled algorithm that is exactly equivalent to a symbolic algorithm, and that would still be system two. And in fact, the symbolic part becomes important only in two ways. We wind up writing anything we do except for our manipulation and gestural knowledge. Most of our declarative knowledge is written as either procedures or statements in natural language. And so the LLMs need to, pre-trained models need to deal with them. And then also, if they're talking back to us, they need to have a symbolic interface. Beyond that, the question is not whether it is symbolic versus neural. I think it's a red herring. It's really a question of algorithms with soundness and completeness properties, whether or not you're able to support that kind of a reasoning. And is that going to just emerge by essentially, in our particular current case, if I train myself on the unrollings of the same algorithm multiple times. The latter at least seems to be a very inefficient way to do it, but it is a good thing for current LLM, LRM technology. And one has to remember that currently this technology has become so powerful that they have won the software lottery. Every company is actually trying to improve LLMs and LRMs, and rather than even other transformer architectures such as universal transformers, which don't have these kinds of length effects built in. But mostly we have the thing that already is working, and we're going to improve this. When is that going to change is anybody's guess. But for now, I would say we should at least understand what they're good for, given the way we are actually doing these things. As again as saying, that's just not full reasoning.
Yeah, so I think that we analyze what we have right now, but let's think a little bit more about the future, no? And we just have a few minutes to do that. So we said that, okay, you have these different techniques. Some of them are providing sound reasoning, some others are providing plausible reasoning. So what's the future here? Is just to use RL to improve LLMs to approximate better and better sound reasoning? Or do we need something completely different, and then the integration of these new, what people call neurosymbolic things, or plausible and sound reasoning? Olga, do you want to start?
Yeah, I personally think that there's no reason to think that we sort of scale our way out of this, right? So I think if we just continue doing what we're doing and scale that up, we will not get anything that provides us with the kind of guarantees that in certain applications are absolutely crucial. I think we need something different there. Which isn't to say that scaling things up and approximating correct reasoning better might not be useful as well, right? But I think it's very important to keep the distinction, right? In fact, I would argue that an algorithm or its implementation, right, a piece of code that's just a tiny bit incorrect could be way more dangerous in practically than one that is grossly incorrect. And why is that? Well, because one, it's obvious to everyone that it's incorrect and we won't use it in certain situations, right? Whereas the other one, it might fail us when we least expect it. And that indeed could be very dangerous, right? And so therefore, I think we're not going to scale our way out of that. At least I don't see why one should believe that. And as a corollary of that, I believe it's very important to be aware that sound formal reasoning techniques exist. And they've also gotten a lot better over the past decade. So progress in AI has not just been in neural network-based AI or machine learning. In fact, there has been substantial progress also in these sort of more rigorous forms of reasoning that actually have been driving technological progress. For example, in computing hardware. So it's important to know that these techniques exist. I think it's important to know, at least for a good population of experts, what they are. We need to continue teaching them. And then we need people who think about how and when to use those, and maybe how to combine them with other forms of reasoning and computation in order to perhaps get the best of both worlds in situations where this is required. Always keeping in mind that there are still many, and there will always be many, many circumstances where very narrow capabilities that can be trusted are actually preferable over broad capabilities that cannot be trusted.
Okay, Rao, do you want to comment on that?
Yeah, I think first of all, I'm not. I don't know why, but I'm not very interested in making prognostications about future. I chose research just so that I can invent future rather than just kind of make random prognostications. But the point I do believe is, I think much of what is happening here is that there is this, I guess, the elephant in the room that we thankfully didn't talk about until now is AGI, or super intelligence, or as I would call ASDI, artificial super duper intelligence, which is my new company. But the question is, what do that all of that hype is based on this idea that there will be like one size fits all solution that would do pretty much everything. And that I don't see it anywhere on the horizon, and it will improve. There is this particular substrate that we are using that might have aspects of other kinds of solvers, verifiers kind of compiled into the generator, but there is no single one size fits all. And another thing that we have to remember is this entire technology is highly, highly dependent on what we provide. So it's like I was saying that yesterday, that Riemann hypothesis will be solved by AI as soon as we find enough proofs of Riemann hypothesis and train the LLMs with that. And I was only being half facetious because in general, this is a memory effect, and it's a useful memory effect because what the humanity knows and what an individual human knows are like so different that the LLMs can bring humanity's knowledge to individual humans. And in that sense, they're amazing productivity enhancing tools. But assuming that somehow they can solve everything, that they will do science, etc., the new discoveries, to some extent, new discoveries are outside of the knowledge closure of the humanity to some extent. And in fact, none of these systems do action in the world. Without acting in the world, you don't get new knowledge. And this is something that's going to be holding them. Unless we find new knowledge and write it on the web so that they can train themselves on it, it's not going to be enough. But what they're extremely useful, and we should use them for what they are good for.
Thank you. Okay, so I think we touched upon and we all dimensions here, and also we took some of the questions and the topics that were mentioned in the chat. So I'll give you just the opportunity to say some final thoughts that you want the audience to remember and to take away from this panel discussion and to, in general, the discussion about AI reasoning. Olger, do you want to start?
Yeah, I think there is a good reason why the chapter on AI reasoning is actually the first in our report. It's not because it's the most important thing there is to say about AI, but it is because it is a pretty fundamental thing, right? And it's a pretty fundamental thing that currently the main thrust of progress is somehow concerned with, but hasn't led to, a really good state of affairs. Has in fact led to a state of affairs that's a bit precarious because people generally tend to overestimate what LLM-based and large reasoning model-based technology can do in that respect, right? So let me be very clear from where I'm sitting. There's three important things. The first is excellent AI reasoning techniques of the kind that provide guarantees exist and are ready to be used and are being used to great commercial success. It's just less visible than what is mostly talked about today. And that's very important. Secondly, they exist and are successful for a very important reason, and that's because there are plenty of contexts where this kind of system is actually needed. Those kinds of capabilities are very much needed. And science and engineering in particular are full of these sort of contexts, right? Where it matters that you can correctly multiply numbers of arbitrary length and precision, where it matters that your sorting algorithm, doesn't just provide something that looks approximately correct, but that is 100% correct, right? And the third point is emphasizing that there are weaknesses in the current technology isn't the same thing as saying the current technology isn't useful. Of course it's useful, right? But there is actually no reason to say we can only have one kind of technology or the other. We actually have both. And what we need to get far better at, in my opinion, is to know currently when to use what kind of AI technology. And that requires knowledge of what there is and what its strengths and weaknesses are. And there we can get better, and we should get better.
Thanks, Olga. So, Rao.
Yeah, I have a very short way of saying this, that think of alchemy. Those people who were alive during the days of alchemy and thought alchemy is the answer basically failed. Also, those people who thought alchemy means chemistry is useless also failed. Alchemy is problematic not because chemistry is a bad area, but because some bozos thought chemistry, when prompted the right way, will become nuclear physics. And that is the distinction I want us to remember. LLMs are great technology, LRMs are great technology. Don't believe that they can do what they are not necessarily designed to do. Ask yourself what should be the limitations and work around them. You want chemistry as well as physics, but you don't want alchemy guiding your research. Thank you.
Thanks, Rao. So let me thank the panelists. I think that this was very insightful and even innovative discussion around AI reasoning. I hope it shed some light or given some food for thought to the audience. Thanks also to everybody for joining us. This panel has been recorded. The recording will be available very soon on the AAAI website for the same website where you find the report on the future of AI research, where you can already found the previous two panels. And also will be available on the AAAI YouTube channel. So thank you all, and I'll see you soon for another interesting discussion. Thank you.